calculator, but I would suggest on a test that you use the calculator to check a calculation that you're doing. This gives you 11, carry 1 over. That gives you a 4 plus 1 is 5, and that gives you a 9 there, and an 8 there. So you're adding place value by place value. These are hundreds, these are thousands, these are hundreds, these are tens. And you're adding tens to tens, hundreds to hundreds, and so forth. So it's just the addition tables that we're used to. One-digit addition tables. Any others?
Minusing, right?
The subtraction is the same, that's right. But you might have to borrow when you subtract. Any others in 4.2?
71.
Okay. Geometric shape here looks something like this. It's labeled. Some of the edges are labeled, others are not. Okay, as usual, we want to get x and y, and then we want to add them all up to get the perimeter. Okay, the reasoning goes like this. You know that this distance right here across the entire thing is 4.875 feet. These two are given, 1.2 and 1.6, so the x is the only other element in this. If we add these together and subtract it from that one up there, we should have x. So it becomes an addition of these two that we do know, 2.8 feet, and then that much gets subtracted from the big one, 4.875 minus 2.8. Now here's a place where the trailing zeros would come in handy, so we just attach them. They don't change anything. They just fill place values. And do a subtraction then, that's a 5, a 7, a 0, and a 2. So that's what this has to be. That's the x, 2.075 feet. Same kind of reasoning goes for the y's. You know that this large side over here is 3.62, and
It's the 1.3
but I forgot to put in a dimension. That's 1.03. Yeah, the way it is, you can't do it. This much right here is given to you as 1.03 feet. So therefore, subtracting that 1.03 from the 3.62 will tell you why. Okay, so that's a borrowing situation. You have to get one from over here, making that a 5. 12 take away 3 is 9, and so forth. 2.59 feet. That's the y. And that's y over here also. So the fact that they have the same letter means that's the same thing. Okay, now we've got all the distances all the way around, and that's a matter of adding the whole thing up, which takes a lot of time, so I'll just tell you what the answer is supposed to be. The total is 22.17 feet, and you can do that on your calculator too. That's a very quick thing to do on a calculator. Just go around 1.2, push the plus button, 3.62, push the plus button, 4.875, you keep pushing the plus button. And then finally at the end you push the equals button. And 22.17 pops out. Okay, any others? 17? Oh, 77. Yes. Okay, they give you a little table there of IBM and FedEx. It's the stock going from January through May of some year. The table gives the closing stock prices in dollars per share for the first day of trading for the given month. By how much did the IBM stock increase between January and May? So you're getting your numbers off the table. So for the IBM, there was an increase, and in May, you have this much, 90.103. .17 per share, and in January it was 97.27. So they want a subtraction, so you can tell what the difference is between them. That would give you the amount of increase. And when you do that, it looks like this. This gives you 0. Borrowing over here, that gives you a 9. The 2 there will cause you to borrow, so a 9 there and a 1 there. That gives you 12, take away 7 is 5, 9 take away 9 is nothing, so that's it, 590. Yeah. The important thing there is the borrowing. And the way you borrow is, since this guy's got no money at all, you go next door, borrow that one, of course it reduces that to 0. So technically you're borrowing $100. And where are you going to put the $100? Well, you want to distribute it so that some of it goes into the tens position, some of it goes into the ones. So you put 9 in the tens position, leaves you $10 that you can put over here. And that 10 plus the 2 that was here from the previous borrow gives you 12. So 12 take away 7 is 5, 9 take away 9 is nothing. So it works. It's a double borrow kind of problem. It's amazing how quickly that borrowing stuff does work. If you just simply write 9s everywhere but the last one and put a 1, you got it. That works.
I got it wrong. By 1.
Any others in 4.2? Okay, let's move on to multiplying decimals. Now, we all remember how to multiply whole numbers. Of course, we use our basic tables, but when we get numbers that are not in the table, that are bigger than the table, 2-digit or 3-digit numbers, then we do a vertical process, and that works very nicely also. There's a carrying process that goes on. Now, when we're talking about decimal numbers, something very similar happens actually. Your book starts out with that. Now, if we were to say that correctly, instead of using the word point, we'd say that as 3 in the tenths position, so that really is 3/10. And this is 41 in the hundredths position, so this is 41 hundredths. So we're going to multiply 3/10 by 41 hundredths. I'm just changing them back to normal fractions because we know how to multiply normal fractions. This will give us some sense of how to do a vertical process. Okay, for this, we would cancel, but there's nothing to cancel. So 3 times 41 is 123. 10 times 100 is 1,000. Now let's switch it back into decimal notation, because this is a decimal fraction. It's got a denominator, which is a power of 10, so that's a decimal fraction. It's very easy to switch. This is going to be 0.123, and it turns out that 3 is in the thousandths position. That's exactly what you need, 123 thousandths. So it works fine. So in other words, this is that. Okay, now we did it by going through fractions, and that's not what you usually do when you're multiplying decimals, but it just justifies the whole process. Basically what happened here is the 3 got multiplied by the 41, and you can see that multiplication going on right here. So you get the 123, and then the second part of the problem is to figure out where to put the decimal point. And you figure that out by taking the denominators and multiplying them. Oh, that's 1,000, so that tells me where the decimal point goes. It goes to the left of the 1, because only putting that decimal point to the left of the 1 will make this 123 thousandths. Okay? So there are 2 parts to a decimal multiplication. One is get the size of the number, and the second is, what do you do with the decimal point? Now, what we do in a yes.
But as I recall, the easier way to do it.
Which I'm going to do right now.
Okay, you go
So
ahead.
just relax and watch what happens. Yeah, right. I'm not gonna leave you with that. This is what teachers use to demonstrate something and motivate it, all right? Because it works through fractions, you know what the answer is. That's gotta be the answer. Okay, then you look at the answer and you say, can I get that any quicker, please? Which is what you were saying, right? Okay, yes, we can't get it quicker. So here it is, this again is called vertical multiplication. Now the first thing you'll notice about vertical multiplication is that the decimal points aren't lined up.
No, they're not.
And that's fine. As a matter of fact, most of the time what you do is just sort of line everything up on the right-hand side. And it doesn't matter where the decimal points are. Because the first thing we're going to do in this process is forget the decimal points. Just pretend they're not there. Now you don't have to erase them or anything, but just in your mind, just say, okay, no decimal points. Okay? How would I do that? Well, I take 3 and multiply it by 1 to get a 3. 3 times 4 is 12. Okay, then zeros, of course, don't count. Anything times 0 is still 0. So we're done. That's quick. Notice it's exactly the same as whole number multiplication. Right? Whole number of 41 multiplied by the whole number of 3 would give you the same answer. Agreed? All right, now we have to put the decimal point in. Well, the quick way of doing this is to simply say, all right, how many place values do I have to the right of the decimal point in each of these factors?
3?
Factors are things that are multiplied, right? They're both factors. All right, so I have 1 here, I have 2 there. What you do is manufacture the decimal point in the result, in your product, so that you have the sum of these two. 1 plus 2 is 3. So it looks like this. 123 normally has its decimal point right there. But you want to manufacture 3 to the right. So you go boing, 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 and put it back here. 0.123. Now, just to be professional, so we do not get laughed out of the cocktail party for the math department, we put a 0 there, right? That's called a leading 0. Nobody cares except mathematicians, and they really care. So that's your answer, 0.123, which of course is that. All right, let's do some bigger ones, more interesting ones, so to speak. 29.3 multiplied by 2.8. Again, no attempt to line up decimal points in general. In this case, they happen to line up, but it's not the usual case. We're just going to multiply 2 whole numbers. That's it. So 8 times 3, 24, carrying 8 times 9.
81.
8 times 9?
72.
Oh, 72. I heard
72.
71. Okay. And 2 is 74, no? 8 times 2? 16 and 7?
23?
23.
23, yes, very good. Okay, so we've got the first multiplication. We've taken 8 and multiplied it by 293. There it is. Okay? Now, we take the 2. Now, remember, the 2 is not really a 2. Well, it is in this, it actually is in the decimal number. But in whole number multiplication, that's not really a 2, that's a 20, right? So we have to remember to shift this one over 1 to the left. So 2 times 3?
6.
6, but the 6 goes there. It does not go over here. Okay? It goes there because it's really 60. Okay, got that? Everyone okay with that?
Yes.
All right. All right, now 2 times 9?
18.
18. So the 8 goes there and 1 there. 2 times 2?
4 and
And
5.
1 is 5. Now you can put that trailing 0 in if you want to, because we're going to add now. You add the 2 results, and that becomes 4 here, 10 there, carrying 8 and 3 is 11, 12, carrying 6 and 2 is 8. Okay, so we're getting 8,204. Now that's not the answer. That's just what happens if you forget decimal points. So we go back and say, well, there's 2 things to the right of the decimal place there. So we're going to make 2 happen here. 1, 2. 82.04 is the right answer. Okay? So it's done in 2 stages. The first stage is whole number multiplication, and the other stage is figuring out the decimal places by simply looking at the original factors. That's how it's done by hand, so to speak. Let's do an extreme one. 2.79 multiplied by a very small number. Now, one of the reasons why I like this problem is because it brings us to something about calculators that most people don't notice. Could you do this on a calculator? Sure you could. But there's a lot of zeros to enter. Well, it's not a lot, but there's enough so that you'd want to watch yourself as you're entering the zeros, right? What if you had, a number which is way out here and all the zeros in front of it? Easy to forget a zero. Easy to not put in the right number of zeros on the calculator, right? Yeah, some people call that mathematical dyslexia or just getting bored with pushing the zero button, whatever, All right, we're forgetting decimal places. They're gone now. Don't pay any attention to them. Just multiply 3 by that top number. 3 times 9.
27.
Got it. 3 times 7.
21.
21 and 2. 21 and 2.
23.
23. Oh, we're getting there. All right, 3 times 2.
6.
And 2.
6, and then 8.
8. Okay. Well, that's it. That's all the multiplying we're going to do.
And then you count over to the right 6 places.
That's right. Because you got 1, 2, 3, 4, 5, 6 to the right of the decimal point in both factors. You add them up, 2 and 4. And so you go boing, all right, 1, 2, 3, 4, 5, 6. There it is over there. What do you put here? Zeros. And then you put your leading 0 there. So there's the right answer. Let's just see if we can say this number. It's a really weird number. All right, you need the place value, right? 10th, 100,000, 10,000, 100,000.
Yeah.
Million, okay? So this is 837 millionths. That's a very small number.
Yeah.
All right. Now, there are some numbers, decimal numbers, which when multiplied by powers of 10 or powers of 1/10 produce quick results to you. In fact, you don't have to do any multiplying at all if you know the tricks. So we're going to look at powers of 10 multiplied by a decimal number and powers of 1/10 multiplied by a decimal number. So here's powers of 10. And you might expect that this is true, by the way, because remember, decimals are base 10 numbers. In other words, 10 is the absolute core of what the decimal system is about. So if you're going to take a decimal number, your book takes 2.7. And it multiplies it by 10. Okay? Now, please, let's use some common sense here. Okay? This is very uncommon in math. We're going to use common sense. All right, if we're multiplying 2.7 by 10, are we making it bigger or smaller? Bigger, obviously. You multiply something by 10, it's getting bigger, right? Is that common sense now? It is now. All right.
Yeah.
So here we go. 7 times 0 is 0. 7 times 1 is 7. 2 times 0 is 0. 2 times 1 is 2, right? And you can put the trailer on there if you wish. Okay, so this gives us 270. Well, not quite, because we haven't taken into consideration the decimal point, right? So let's go back and do our decimal point thing. There's 1 to the right of the decimal point. So we take that 270 and shift it over so that there's 1 to the right of the decimal point. So this is 27. Well, does this make sense? I took 2.7, multiplied it by 10, I get something bigger, 27. Makes sense, right? All right. This stuff has got to make sense or something, some calculation could easily get out of hand. Let's make it bigger. Suppose we do 100. 2.7, multiplying. Again, forget the decimal place, just multiply 100 times 27. and you can put the trailer in if you like. 2,700. Okay, except now we have to calculate the shift to the decimal point. Starts here, goes 1 over 270. Okay, we'll do one more just to get the feeling of the pattern here. 1,000 multiplied by 2.7. That's 0,007, 0,002. Adding. Okay, shifted over by 1, 2,700. All right, now that's all fascinating. Obviously, it obeys the rules we just talked about. But is there a quicker way? Yes, there is. If you take 2.7, multiply it by 10, all it effectively did was shift that decimal point 1 to the right. There it is. It went from between the 2 and the 7 over here to the right of the 7. Okay? Here we multiplied the same number by 100. It shifted the decimal point. Well, it's got we multiplied 100 by 2.7, and effectively we shifted the decimal point 2 to the right. This was a shift of 1 to the right. Here we multiplied by 1,000, 2.7, decimal point shifted 3 to the right. All right, so the decimal point, when you're multiplying by powers of 10, gets shifted to the right the number of times that there are zeros in the power of 10. So here's 1 0, shift over 1. 2 zeros, shift over 2. 3 zeros, shift over 3. So if I was taking, let's say, 2.7 and multiplied it by 1,000,000, that's a power of 10. That's pretty obvious, huh? How many zeros do I have? 1, 2, 3, 4, 5, 6, right? I take the 2.7 and go 1, 2, 3, 4, 5, 6. Put in the zeros and rewrite it with the little period markers. This would be 2,700,000. So no calculating at all. Just shifts the decimal point when you multiply by powers of 10. And the important thing is to know that you shift it according to the number of zeros you have in the power of 10. We had 6 zeros over here, got shifted 6 to the right. Everyone okay with that? It's making your job a lot easier when you got powers of 10. So if we have something like this, the Earth-Sun distance is on the average about 92.9. They write it this way. 92.9 million miles. Now that changes during the year because our orbit is not a circular orbit. It's basically an elliptical orbit, so there are times when we're further away, times when we're closer, and so forth. And that, of course, has something to do with our seasons and whatnot. All right. By the way, that's a long distance. And it's very good that it's a long distance. We don't want to get too much closer. I mean, Venus is not a vacation spot. Okay. We don't do this calculation, but not in this class, but later on we do it. We take that distance, 92.9 million miles, and we take the speed of light. And we do a calculation that tells us the time it takes light to get from the sun to the earth. It's really quite amazing. It's much more than you might think. 92.9 million miles. Even light doesn't go that fast. You know, it takes about 8 1/3 minutes for the sun's light to get here. So when you go out there and look at the sun, not for too long, you're looking at the sun as it was 8 1/3 minutes ago. It's not the sun the way it is now. Interesting, huh? How about the stars? Oh, much, much longer, right? This is why astronomers talk about light years. Light years have nothing to do with time. They have to do with distance. It's the distance light travels in 1 year, which is huge. It's about 6 billion miles, okay? But when you look at some of those stars, they're said to be 1,000 light years away. That means that it takes light 1,000 years to travel here from that star. So you're looking at the star the way it was 1,000 years ago. We don't see the stars the way they are today. That sky is a time machine. We're looking back into time because of the distances involved. Okay, how would we write this? Well, if we wanted it as a regular number without the word million in it, we'd write it as 92.9. Now, a million, we just saw, has 6 zeros, right? So we want to put 6 zeros on here. We want to move that, we want to move this 6 to the right. 1, 2, 3, 4, 5, 6. Put the decimal point over there, take it away from there. 1, 2, 3, 4, 5 zeros. Okay, so that's 92,900,000 miles. There it is in standard form without using the word million. Okay? All right. Now we're going to look at powers of a tenth. It's pretty much the same thing. Now I'm going to write a tenth that way. That's the decimal way of writing 1/10, right? That's 1 in the 10th position. Agreed? Everyone okay with that? Right. Let's see what happens. So, let's say we take 0.1 and multiply it by 2.7. Again, multiplying. We just agreed decimal multiplication. We are not going to even recognize the decimal points. We're just going to ignore them and multiply what's there. So 7 times 1 is 7, and that's it. And 2 times 1 is 2. Again, shifted over 1 to the left because it's really a 20. Okay, so this becomes 27. Now, count the number of places to the right of the decimal point, add them together, that gives you 2. Take that 27, force it to have 2 places to the right of the decimal point. 1, 2. It becomes 0.27. Does this make common sense? It does, because you know that if you take 2.7 and multiply it by a tenth, effectively you're dividing it by 10. Multiplying by 1/10 puts the 10 down in the denominator and divides the number by 10. It's going to make it smaller. Is 0.27 smaller than 2.7? Yeah, it is. It's going in the right direction. Notice what happened. Look up here, you got 1 digit to the right of the decimal point in the power of 10, of 1/10 rather. You got 1 digit to the right of the decimal point in the power of 1/10. Okay, effectively it took the 2.7 and shifted the decimal point from where it was over this way to get a 0.27. Now let's see if it keeps on going. Suppose we do 0.01. That, by the way, is 0.1 squared. If you take 1/10 and multiply it by 1/10, you get 1/100th. There it is, 1/100th. Okay, now multiply your 2.7. All right, ignore the decimal points. 7, 2. Okay, put it in there. That gives you 27, but you've got 1, 2, 3. 1, 2, 3. It becomes 0.027. Now, speeding it up, you've got 2 digits to the right of the decimal point in the power of 10, and we moved it to the left, this way. So it becomes 0.027. So what you might expect is when you go to 1,000 and multiply by 2.7, you just might as well take the 2.7 and do 1, 2, 3, 1, 2, 3, becomes 0.0027. So multiplying by powers of 1/10 moves the decimal point to the left. And how many spaces? The same number of spaces that you have in the power of 1/10. Now, this is spaces. This is not zeros. Okay? I have 2 spaces here. I moved it to the left over there. And there it was. I started with 2.7, moved it 2 to the left. There you go. 3 spaces here, 2.7, move it 3 to the left. So if you have, let's say, something really ridiculously small. Okay, you've got 1, 2, 3, 4, 5, 6. If you take 2.7, no need to multiply at all. Just shift it to the left. The same number of times you have spaces to the right of the decimal point in the power of 10. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 0, 0, 0, 0, 0. That's it. The difference between the two techniques is this. When you're multiplying by a power of 10, you shift the decimal point to the right, the same number of zeros that you have in the power of 10. When you're multiplying by a power of 1/10, you shift it to the left, the same number of digits that you have in the power of 10. So that includes the 1. When you're dealing with powers of 10, it does not include the 1, it just includes the zeros. All right. Those are common enough that we should know those two rules. So you ought to be able to multiply things that have powers of 10 or 1/10 very easily. Let's do an applied problem. That's more important, actually. Jane Marie bought 8 cans of tennis balls for $1.98 each. She paid $1.03 in tax. What was the total bill? Okay, I hesitate to do this, but I do have to make sure that everyone understands how bills are actually charged at the cash register. Because you could have a wrong idea about it. She's buying 8 cans of tennis balls. Each one is $1.98. So it gets scanned, and unless they have the ability to use a multiplier, they'll scan it 8 times, right? And then, after that, the cash register calculates the tax on 8 of those cans. But that's only added in once, right? It's not added in the whole time. So, the way we would do this problem is the following. We'd say, okay, I've got 8 is the number of cans of tennis balls. $1.98 is price per can. And the amount of tax is $1.03. It's a 2-step problem. You can't do it in 1 step. You simply say, okay, I'll figure out how much the total cost of the tennis balls is. So $1.98 times 8. 8 times 8 is 64 and so forth. 9, 72, 78. 8 and 7 is 15. 1, 2. 1, 2. 1584 is the actual cost of the tennis balls. And then the governor comes in and says, oh, I want some money. He does this every time we buy something. He's right there with us, watching what we buy. You know that Amazon now charges tax? Everyone knows that? That's very recent. That's only a few months ago. Because California started saying, sorry, you're going to have to pay tax. So now, with that, we have to add the tax. Now, usually most cash registers will automatically calculate tax on that amount. Okay? Now, this is not the percentage we have here. We have about 10%, 9.5%, I think, is Monterey. Something like that.
Depends on the city.
And this is not 9.5%. It's a bit more than that. All right, so 1.03 would be the amount of tax. That would have to be added. So we get this, 7, 8, and 1687. That's what we get from the person behind the cash register. 1687, please. So that's how the whole thing works there. Has anyone ever seen the Mona Lisa in person?
No.
It's in the Louvre. It's a very interesting painting. It's created a lot of stir among artists. It's not very big, it's rather small. And we're going to calculate its area.
She's an ugly woman. She's an ugly woman.
Is she really?
Yeah,
Okay.
she's ugly.
Well, beauty's in the eye of the beholder, so you know. I went there to look at it, and there were a few hundred tourists in the room, so I got to stand against the back wall, and I couldn't see it at all. So I mentioned it to the person who was there, and he said, oh, don't worry, come on, I'll show you a much better one. So we went around the wall, the back wall, into another room, and there was another portrait by the same artist. And it was much more beautiful, that's for sure. Now, maybe it was the person, I don't know. But the point is, he did a lot better work than that. Mona Lisa is not his best work, but it's the famous one, right?
The reason it's famous is because people never smiled in pictures in that time period. So one oddity was it had a little bit of a smile.
Very little.
Very little.
Very
But
little.
compared to the frowns you get or the seriousness you get other people, it was
Yeah.
revolutionary.
Okay, so it's a breakthrough. Oh, that's a nice way of justifying it.
That's a big
Some people thought
All right,
the
you say
Vinci
so.
painter himself had Mona.
All right, here it is, Mona Lisa. I'm not going to draw it, don't worry. All right. It says the dimensions of the painting are 30 inches, we'll call this the 30-inch side, by 20.875. Maybe something like that. Actually, let's take a second just to find out how big it really is. All right, here's the real Mona Lisa size. Here's 30 inches, pretty accurately. Okay.
Is that the outside of the frame?
No, this is just the actual painting itself.
Really?
Yeah. 20.875, well, that's going to be something like this.
I'm curious, how much does it cost for the Mona Lisa? Do you know how much it's worth?
Millions
It is
and
probably one of the few things on earth that is priceless.
yeah.
I mean, don't even ask.
It's like American Express.
It's not for sale.
It's not for sale, that's right. So there is pretty much what it would look like if we had it right here in the room.
Is that on its side? Or is it really wide? I don't remember it being wider like that.
White?
Wider.
Oh,
like,
wider.
than it is
No,
tall.
that's it. I just measured it, so there you go. Okay, 30 inches and 20.875 inches. All right, what we're going to do today is figure out how much area there is. This is in inches also. Okay, so area is length times width, huh? This is the length. The longer side is always the length. The width is the shorter side. Okay, so we have to multiply 30 times 20.875. And let's do it vertically. Okay, that's what we're doing. So here we go. 5 times 0 is nothing, 15. Okay, 7 times 0 is nothing. 7 times 3 is 21. And that's it. 8. 8, excuse me, let me get rid of that. Okay, 8 times 0 is nothing. 8 times 3 is 24. And that's 0, so we don't even have to worry about it, except we have to shift the thing over twice. 2 times 0 is 0. 2 times 3 is 6. Okay. So now, adding all these things up. 62.556. Okay. Well, I'll have to put it in the right place. All right, now let's calculate the number of places to the right of the decimal point. 1, 2, 3. Here's the decimal point. Make 1, 2, 3. So it's 626.250, and that would be in square inches. 626.250 square inches for the Mona Lisa. That size right there. The really weird part about it is, perhaps you've seen this on YouTube or something. Here she is, you know, smiling. You've got a line of trees or something over here, and then the line is over here. So you say, well, what happened behind her head?
I think
An
it's
earthquake?
illusion.
What?
That's what like makes her look like she's smiling, is because you see like the off
Yeah.
levels in the background.
Yeah.
You can't tell.
So there's your art lesson for you.
Oh.
There's multiplications to do, so it doesn't matter what order. Everyone hear what Leah just said? She said, could you put this bigger number on top and put the 30 on the bottom? Sure. It doesn't matter, because you multiplying, you can commute, so it's perfectly okay. All right, this is section 4.3.